So today I want to basically try and finish off with a quick survey of a couple of Higgs extensions beyond the standard model. I'll look at models with an additional Higgs doublet and an example with Higgs triplets. And I'll try to get through as much of this as I can in before 10:15. But if I wind up skipping some things in my notes, I am going to give my notes to Susan to scan and put on the wiki, so you can always look there for a few details about, probably I'll skip the bit about the different types of two Higgs doublet models. Okay. So the idea here, so I'm going to start with the two Higgs doublet models. Okay. And the idea here is that we just duplicate the Higgs sector. So in addition, you just add a second doublet, right? So we're going to have two doublets, phi1 and phi2. So just to establish some notation. Okay, I'm just to establish what I'm going to use later on. And then the same thing with phi2. These are not mass eigenstates here that I'm writing. We'll see where how the mass eigenstates come in a little while. E2 plus 8. Okay. Both of these are SU2 doublets. They both carry the same hypercharge 1/2. I've already implicitly made two assumptions. One is that the vacuum expectation values of both of the states are aligned in charge space. So they're both in the neutral components. You want this so that you don't break electromagnetism, right? We know the photon is massless, electromagnetism is an unbroken gauge symmetry. Your model better respect that, okay? The second assumption I've made is that the phase here is the same, okay? This is, you can always choose a basis in which that is true. But I'm going to assume there's no CP violation. If there is CP violation, then the neutral states, there's three physical neutral states, they all mix with each other. If there's no CP violation, you wind up with one CP odd and two CP even. Yeah? Yeah. It's basically because you only break 3 of the generators, and you can always identify the 4th with the photon. Yeah. Here, actually, I think in general you can break charge by basically, if you choose the parameters in such a way, you can break charge, but you don't want to be doing that, essentially. Yeah. Mm-hmm. So the hypercharge. So I should say two things about the hypercharge. So if I were to define these with y equals -1/2, I'm free to do that. That's just the conjugate representation. In supersymmetry, that matters because you write a chiral field and you don't use the adjoint of the field. This is called hermiticity. And that actually dictates the structure of the fermion couplings in supersymmetry. I guess the second comment is there's two conventions for defining the hypercharge, one where you factor out that 1/2 and one where you don't. I'm not sure if that's what you have in mind. Yeah. So I could define this guy with hypercharge 1/2 and then write a, so I could define is that what you have in mind? Yeah, this is how it's done in supersymmetry actually, but for technical reasons of making the fermion couplings. And it matters in SUSY because of the analyticity requirement of the superpotential. But in non-supersymmetric models, it's totally irrelevant, basically. So yeah, you can always define your phi2 tilde, right? The conjugate. Okay. Yeah. Okay, so let's count the states. That's generally the first thing you want to do. So the degrees of freedom, we've got two complex charged scalars. Okay, and they're antiparticles. We've got two CP even real scalars, real neutral scalars, H1 and H2, okay, the way I wrote it here. And we have two CP odd neutral degrees of freedom, A1 and A2, okay? And we still have to identify the Goldstone bosons. There's going to be one complex charged scalar which you can gauge away, and there's going to be one CP odd neutral scalar which you can gauge away, just like in the standard model. So one linear combination of these is going to be the Goldstone boson, okay? The other linear combination is going to be a physical charged state, so I'm going to call it H, big H, plus minus. Similarly, for the CP odd guys, one linear combination is going to be the Goldstone boson. The other linear combination is going to be a physical pseudoscalar, which we'll call capital A. These guys also mix in general to form mass eigenstates. The names I'm going to give these are little h for the lighter one and big H for the heavier one. And you know, how you identify these is a little more complicated than how you identify the Goldstones, but I'll just make some comments on it, okay? So the first thing we want to do is identify the Goldstone boson so that we can learn what are the remaining physical degrees of freedom in the theory. And there are at least three ways to do this, to just determine which linear combination of these states gives you the Goldstone. So the way I learned first, okay, which is not necessarily the most efficient way, is, so we want to identify, this is a weird piece of chalk. Okay, so we want to identify, I'm going to use the other one. We want to identify the Goldstone bosons, okay? There are at least three ways to do this. Probably the most sort of following your nose way is to write down the scalar potential, okay, the most general gauge invariant or invariant under the symmetries that you've imposed potential involving those two fields. Find the minimum of the potential so that you learn what V1 and V2 are in terms of the other parameters of the potential. And then write out all the mass terms in terms of the physical states, plugging in V1 and V2. And get a gigantic mass matrix for all those states. It's going to be block diagonal because, for example, you're not going to get mixing between a charged state and a neutral state. That would violate charge, okay? And then just identify the masses, identify all the mass eigenstates, and pick out the massless particles, and those are going to be the Goldstone bosons, and everything else will generically be massive. Okay, so that's one way to do it. The second way you could try to do it is to write down the SU2 cross U1 gauge transformations from, I guess, my first lecture. Yeah, probably my first lecture. Apply them to these two fields. So when you apply a gauge transformation, it's the same transformation to that field and to that field with the same function, alpha of x, okay? Because you're doing a gauge transformation. It affects all things with the same gauge charge in the theory. And then try and work out which linear combination you can gauge away, okay? Which is a little tedious, right? The third approach to identifying the Goldstone bosons is this following trick, which I want to show you just because it's handy and useful, okay? So before I show you the trick, let me consider one more time the standard model Higgs gauge kinetic terms. Right? So we've got in the Lagrangian, there's our d mu phi, okay? And the covariant derivative that's going to act on the Higgs looks like the following. I'm writing it in terms of the sigma plus and sigma minus matrices, which are those guys, okay? All right, I'll just write the thing. Okay, Q is the electric charge. And I'm going to apply this to the Higgs field. And let me write out the full Higgs field, not in the unitarity gauge. So let me keep these extra modes, because this is the analog of what I want to do with the two Higgs doublet model. Okay? And so let me look for a certain set of terms in this covariant derivative, in particular terms that involve one derivative, okay? One gauge field, so a W mu or a Z mu, okay? One scalar, so one factor of the scalar field, and one vacuum expectation value, okay? These terms are basically going to be terms of the form d mu phi with a V in front, W mu, okay? Which is a really weird vertex. It's like a scalar that turns into a gauge boson with a derivative on it, which gives you some momentum factor here, okay? These are not physical interactions. These are things that disappear when you go to unitary gauge, because you gauge away the fields that actually participate in these interactions. Only the Goldstone bosons participate in these interactions, and this may be why people call it eating the Goldstone bosons, because you have this weird mixing term here of the Goldstone and the W, and then you go to the appropriate gauge and the Goldstone part disappears, right? So the fields that participate in this type of interaction can be identified as the Goldstone bosons, because physical fields don't do that. Physical fields stay mass eigenstates. They don't convert into a gauge boson halfway through the universe, okay? So let's write out those terms. When I apply the derivative, okay, derivative acting on V is 0. So the term in which I'm going to take the derivative, okay, is going to have the field in it. And the other term with the gauge boson is going to have the VEV part of this doublet picked out, okay? So let me write those down. The Lagrangian is going to include, so if I take the derivative in this first term, I can write the following. Okay? And then I'm going to multiply, oops, stagger. Okay? And then I'm going to multiply that by a term where I just take gauge modes, okay, acting on these fields, okay? Oh, sorry. I'm just going to take the gauge modes, and in this doublet, I'm just going to take the vacuum expectation value part because I want a V in my expression. So in the upper component, I can apply this raising, this sigma plus to the doublet and pull a V up into the upper component. Okay, and in the lower component is electrically neutral, so Q is equal to 0. I'm just going to get the following thing. T3 for the lower component is -0.5, and then here's Z mu and the VEV. Okay, and then I have a second term, which is essentially the reverse term, where I put the vacuum expectation value in the first doublet and then put the field in the second doublet. Okay. So this thing, Hermitian conjugate, and then the derivatives in this side. Yes. And there's a root 2 there in the denominator. Okay. Okay, so if you multiply this out and collect terms, what you wind up with is the following. Yeah, okay, I'll write it out. So from the first term here, okay, I'm just taking this thing, Hermitian conjugate, and multiplying it by the other side. Okay, so here's a term in which phi plus and minus are becoming a W, or turning into a W sort of. Okay, and then from the neutral parts there are two terms as well. Okay, whoops, the 1 over root 2 d mu h plus I d mu a, minus, sorry, because of the Hermitian conjugation. Let me make sure I'm doing this right. Okay, and then from the second term, I get the same thing with a minus sign out in front. From this minus sign times that minus sign times the Hermitian conjugate of the I. I missed a factor of 2 here. Okay, there's factor of 2. And then here I have d mu h plus I d mu a. Okay, and these should be upper mu's, but it's flat space, so it doesn't really matter. Okay. Okay, so when you add those two terms together in the lowest line, the h pieces cancel, the a pieces add. So the h disappears from this interaction, and all you have left is an interaction involving the pseudoscalar. So this last line becomes just a 1 over root 2 EV over SWCW sine and cosine of the Weinberg angle d mu a d mu. Okay, so the pseudoscalar participates in this weird interchange with the Z boson, but the H field doesn't. Okay, so when you do the gauge transformation to the unitarity gauge, all these weird terms disappear, which is good because they're interactions which indicate you're not working in the basis of states that propagate unchanged. Okay, so now let's do this in the 2 Higgs doublet model. All right. So if you do exactly the same thing, okay, you get one set of terms like that for phi 1, a second set of terms like that for phi 2, and you can sort of just extrapolate based on what I've already written down. The W interactions are going to look like the following. Right, where I have V in the standard model, I have V1 for phi 1 and V2 for phi 2. Okay. Okay. The second term there is just the Hermitian conjugate of the first term, so let me just write plus Hermitian conjugate. And then the last term down here, I lost an I. No, I didn't lose an I. I multiplied the I in front of the d mu a by the I in the front of this term. V over SWCW derivative of V1 A1 plus V2 A2 Z mu. Okay. And no term involving the photon because the photon stays massless. All right. So essentially what I've just done here is identify the states that have to be gauged away when you go to unitarity gauge in order to get rid of these weird scalar and gauge boson interchange diagrams. And you can see, you can just read off immediately what linear combination of phi 1 minus and phi 2 minus and what linear combination of A1 and A2 that's going to be. So if you normalize these things properly, what you get, move over here where there's more space, is the charged Goldstone boson. I have to divide out by basically the coefficient here. I want to be not V. I want it to be just, some sine or cosine, some things that are going to, you can square them and sum them to 1. So let me divide by square root of V1 squared plus V2 squared. Oops, squared, sorry. Okay. Okay. And I can rename these coefficients as mixing angles because if you square them and sum them, they add to 1. Okay. So let me call this one cosine of some angle beta plus sine of some angle beta by 2 plus minus, okay? And similarly for the neutral guy, right, it's the exact same linear combination with a V1A1, V2A2. This is just going to be C beta A1 plus S beta A2, okay? And this angle, you can write the tangent of it in a handy form, is V2 over V1. Okay, and this quantity shows up a lot in two Higgs doublet models. This is the famous tangent beta, okay? This method always works. In two Higgs doublet models, it's, you know, you can basically memorize this faster than you can rederive it. When you're dealing with models with larger representations of SU2, this is particularly handy because the, what happens to a field when you act on it with the raising and lowering operators is different for different representations. And you know, what happens to a field when you act on it with T3 plus minus S squared WQ is different for different representations. So you might get different coefficients in the charged part and in the neutral part when you're dealing with doublets plus other representations that are larger than doublets. Okay, but this is, you know, working in general. And then we can just really easily write down the orthogonal states. So the state orthogonal to that is going to be our charged Higgs. And I've chosen it up to a sign, right? So basically, if I take this and dot it into the G plus minus, I get 0. They're orthogonal. And then the thing orthogonal to the neutral goldstone is going to just look like the following. Oops, A. Okay, so far so good, right? The charged Higgs in a two Higgs doublet model is always a mass eigenstate because there's no other physical, charge 1 scalar that it can mix with. So it's always a mass eigenstate. This guy, if there's CP violation in your model, this guy can mix with H1 and H2, the two CP even neutral components, because it's neutral, right? So they can mix if CP is violated. If CP is conserved, this guy's also a mass eigenstate. Okay. And then finally, if CP is conserved, I can just write out the mass eigenstates little h and big H of the CP even neutral states in the following way. And this is just a definition. So I'm defining a new angle alpha, which I haven't, said what it is yet, but whoops, C alpha H2. And then big H is the state orthogonal to that. Okay, and this is the convention that's used in the MSSM, just to keep everything sort of in the same convention. Okay, so the angle alpha here, the mixing angle, and the masses of these 1, 2, 3, 4 physical states, okay, will be determined by the parameters of the scalar potential. So I haven't written down a scalar potential, but once you do, you can make mass matrices and diagonalize them and get the physical masses and get that mixing angle alpha. Okay, so that's great. Rather than write down the scalar potential, I want to actually look at Higgs couplings. I want to just sort of like follow our noses and do the W, Z, and fermion mass generation, the same as I did in the standard model, and work out their couplings to the Higgs, and use that to illustrate some features of two Higgs doublet models. So you can do this now in full gory detail. It's just kind of, cumbersome. I'm going to focus for the W and Z. I'm going to focus on the couplings to the CP even neutral states. I will leave it as an exercise to work out the couplings to the charged and the CP odd state, but it's fairly straightforward once you have, the covariant derivative. Okay. So looking at the gauge kinetic terms. Okay. Okay, so starting here, you can basically just go and plug in. I'm just going to write down the part involving little h, big H, and the VEVs. For anyone who doesn't know, VEV stands for vacuum expectation value. I hope I defined that earlier. Okay. Right. So, all right. So you plug in, you multiply out. Okay. You plug in this sine and cosine alpha and all of that. What comes out? Well, actually, yeah. Let me do it in the original basis first. So if you plug this in, okay, these kinetic terms include the following pieces. Okay, so some derivative terms. Well, let me write these out and then I'll sort of comment on what happens when you go to the basis of the mass basis. Okay. H1 plus V1 squared. All right. And then similar thing for the Z couplings. G squared plus G prime squared. And then a similar thing as the square brackets, Z mu, Z mu. Okay, I shouldn't say similar, I should say identical, right? So exactly the same expression in these square brackets gets repeated here, right? So first of all, okay, the kinetic terms. This, oh, it's on the other board, drat. Okay. This mixing, this is just an orthogonal transformation, okay, or unitary transformation. It's, it's just a rotation in a two-dimensional space. If I take terms like d mu h1 plus d mu h2, and do that rotation, you're essentially, the coefficient of those two things is the same. If you do a rotation, it doesn't matter, you get little h and big H in the same form with, again, the same coefficient. It's like rotating a unit matrix, practically. So you do this unitary transformation. The first term, let me call that 1, okay? The first term is just going to give you that. If this looks at all mysterious, I encourage you to just write it out. And, the cross terms will cancel, and the non-cross terms, you'll get a sine squared plus cosine squared, which is 1. So it takes like 3 lines, but I'm not going to do it now just to save time. Okay. So that's the kinetic terms. They're, they're diagonal, they're fine. Okay. For the masses of the W and Z, I'm basically going to take the V squared pieces out of the second and third lines of that expression. I'll try to erase more efficiently. Okay, so for the masses of the W and Z, we just want to take the pieces with the V's, okay? And the masses are basically going to come out. So if I look at the coefficient of the WW term, I've got a 1/4 G squared, V1 squared plus V2 squared. And this, remember, in the standard model, looked like that. So you learned that the sum of the squares of the vacuum expectation values of these two doublets had better add up to the standard model Higgs vacuum expectation value squared if you want to get the W mass right. Okay? So that's the thing you learned from this. And you can do exactly the same thing for the Z mass. Remember, the coefficient of Z mu is 1/2 mz. So you get a 1/4 in the actual mass. And it has exactly the same form as in the standard model, right? And you get the same, you get the same relationship between v1 squared and v2 squared in the standard model Higgs vacuum expectation value. Okay, so those are fixed. Tangent beta is a free parameter because you know the sum of the squares, but you don't necessarily know the ratio. Right? Okay, so that's the masses. Now let's look at the 4-point couplings. So couplings of this form. Scalar, scalar, gauge, gauge. Okay? These couplings come from taking the h1 squared and h2 squared terms in these square brackets. Okay? So the Lagrangian is going to contain for these 4-point couplings something like that. And then a really similar looking term for the ZZ coupling. And I can go to the mass basis. I can again do this rotation. If you think of this as a vector space, h1 squared plus h2 squared is the square of the length, the distance from the origin in an h1, h2 vector space. Here I'm doing just a rotation in that vector space. That's length preserving. And so when I transform to the other coordinate system, this is going to give me exactly the same expression, but involving little h and big H. Right? Again, if you don't believe me, you can plug it in. It's literally like a 2-line calculation. And you get this expression, right? And if you compare this to the standard model expression, which is just one of these terms, you can see that there's a coupling of little h to WW, okay, with the same strength as in the standard model. There's a coupling of big H to WW, again with the same strength as in the standard model, okay? And there are no cross terms, so there are no mixed couplings. So there's no little h, big H, WW coupling because they're orthogonal. Okay. Okay, so far so good. Where things get interesting is when you look at the 3-point coupling. So a coupling of one scalar to 2 W's or 2 Z's. Okay? So if you look at the 3-point coupling, the relevant Lagrangian terms are going to look like the following. So let me look at the term involving W plus W minus. I want the cross terms, the 2H1V1 and the 2H2V2 terms from those squares. So I'll pull a 2 out front and write 1/2. Okay, and then the ZZ term is basically identical. Okay, where am I? Yeah. Okay, and then I can rewrite this. So I want to eventually compare this to the coupling of the standard model Higgs boson, right? So I can use the fact that I can rewrite V1 using this expression here, okay, as cosine beta times this square root, right? But this square root, if you look up there at the masses of the W and Z, square root of V1 squared plus V2 squared is just V standard model, right? Right? And now likewise, I can write V2 as sine beta times V standard model. Okay, so that will let me re-express this in terms of V standard model and compare it more easily to the standard model Higgs couplings. Okay? And then I also want to go to the mass basis, so I'm going to write H1. So I just want to invert this rotation. H1 is minus sine alpha H0 plus cosine alpha big H0, okay? And H2, I can basically just read it off, right? It's cosine alpha little h plus sine alpha big H. Okay. Okay, so that means, so let me just focus on the thing in the square brackets. What can I erase? I guess I'll erase this stuff. So let me just focus on the thing in the square brackets, right? Chalk is a little weird. Okay. So this is going to be, actually, let me, in the interest, well, no, I'll just write out. So if I plug in these things and collect terms, I'm going to get VSM little h. There's two pieces, right? So there's the V1 piece, which has a cosine beta times a minus sine alpha. And there's the V2 piece, which has a sine beta times cosine alpha. So this is going to have a coefficient which is that, okay? And then for big H, you can do a similar identification of terms. And then if you go and look up some trig identities, you can actually rewrite this as this combination is actually sine beta minus alpha and oops, big H. And that combination is cosine beta minus alpha. Okay, right. So what you learn is that the coupling of little h to WW, and then the couplings to, oops, the couplings to ZZ follow exactly the same pattern. Okay? This is just equal to the standard model coupling, because when you pull out this VSM, you just recover exactly what you would have gotten in the standard model. But with a modification factor, which is sine beta minus alpha. Okay? And then similarly for big H, you get the exact same thing with a modification factor which is cosine beta minus alpha. Okay? And so if you look at, so these are the new pieces basically. So if you look at these couplings of one scalar CP even particle to a W boson pair, the squares of these couplings add up to the standard model coupling. Often people describe this as the coupling is shared between these two states, and it's really just this, one is a sine, one is a cosine, okay? The same structure comes for the Higgs to ZZ couplings, exactly the same structure. So how do we interpret this? Well, basically, let's look at what happens. So I'm going to want to, okay, right. The idea here is if you have two Higgs doublets, probably you've discovered the lighter CP even neutral Higgs, okay? And then this heavier guy is out there somewhere, right? The couplings of this lighter CP even neutral Higgs seem to be fairly consistent with the standard model Higgs couplings. That means you want to be close to the limit where sine beta minus alpha is equal to 1. And then cosine beta minus alpha is pretty small, okay, if you're close to that limit, right? That limit constitutes beta minus alpha equals pi over 2, okay? So the idea is that so in this limit, sine beta minus alpha is 1. Cos beta minus alpha is 0. Okay? And if you're close to this limit, sine beta minus alpha will be close to 1, and cosine beta minus alpha will be close to 0, but maybe not exactly 0. Okay? So in this limit, the goldstones, so we've already written out what the goldstones are. Okay? Actually, I think I erased it. Did I erase it? Goldstones. Yeah, I did. Right. So our goldstones are this combination. Okay? And similarly for the neutral goldstone. If you look at little h, okay, when you identify when you set alpha, okay, when you set beta minus alpha equal to pi over 2, that means that alpha is beta minus pi over 2, okay? And you can plug that in here and here, and what you wind up with is okay, if you think about the sine and you go back by pi over 2, and then you flip you flip, okay, all right. You can look up some trig identities, right? This is just identically cos beta h1 plus sine beta h2, okay? So this limit, when beta minus alpha is equal to pi over 2, the sine beta minus alpha goes to 1 limit, corresponds to little h living in the same linear combination of phi 1 and phi 2 as the Goldstone bosons, and actually as the whole of the VEV as well. So you can write a linear combination of phi 1 and phi 2. You can basically write cos beta phi 1 plus sine beta phi 2. Okay? Let me call that phi h. I'll explain why in a second. This is going to have the Goldstone bosons in it. In this limit, okay, it'll contain little h. This linear combination, if you plug in cos beta v1 plus sine beta v2, you get v1 squared in the numerator, v2 squared in the numerator, over v1 squared plus v2 squared square root. You just get v1 squared plus v2 squared square root, which is the standard model Higgs VEV. And then the neutral Goldstone is in here as well. Okay? And the orthogonal doublet so minus sine beta phi 0 plus cos beta, phi 1, plus cos beta phi 2. Let me call that phi 0 to reflect the fact that it's going to have 0 vacuum expectation value. Contains the charged Higgs. It contains big H. When you rotate the vacuum expectation values this way, you get 0. Okay? And it'll contain the thing orthogonal to the neutral Goldstone boson as well. Okay? So in this basis, you can essentially identify this as the standard model Higgs doublet, and that is just some other scalar doublet that doesn't participate in electroweak symmetry breaking and is just out there. Okay? H here stands for Higgs. This is sometimes known as the Higgs basis. And is a convenient basis for working in, just because you know where everything is. Okay? When you're away from this limit, this sine beta minus alpha equals 1 limit, what shows up down here is actually little h sine beta minus alpha plus big H cos beta minus alpha. Okay? And what shows up down here is minus little h cos beta minus alpha plus big H sine beta minus alpha. Right? So sine beta minus alpha basically parameterizes how far you are from little h living entirely in the doublet where the vacuum expectation value resides. Okay? And so this picture can kind of give you intuition for the couplings of these states to gauge bosons. For example, if I want to look at couplings to a single W, okay, right? W couplings to a SU2 doublet let you transform the upper component into the lower component. Here it's just Goldstone, so it's not physical states. But over here, you're going to get couplings that look like W, H, say, big H, right? Or W, H minus, and A, right? Those sorts of couplings. Okay, and similarly, you can get couplings of Z to the A and whatever else resides in the same doublet. So for example, if you want little h, right, this is going to go like cos beta minus alpha. Okay, so it goes to 0 in this standard model-like limit. Okay. So this is kind of a convenient way of thinking about things. So before I run out of time, I want to say some things about fermion mass generation, which is also very interesting in two Higgs doublet models. And yeah, and I'm going to skip some details in this, but it'll be in my notes, and I'll give them to Susan to scan and put on the wiki, so you can look at this in your free time later on. bigger piece of chalk. Okay, all right. Okay. Okay, so we want to make fermion masses. So the most general gauge invariant thing that you can do is just take the standard model fermion mass generation terms and duplicate them, once for phi 1 and once for phi 2. So you can write down fermion couplings, which look like, for example, this is a really weird shaped piece of chalk, D, and I'm going to put a number 1 here, a subscript 1, to indicate that this is a coupling to phi 1. Okay, right? And I can add a second term here, D2. So these are two separate matrices. Like that. And then similarly for the uptype quarks and the charged leptons. Okay? Generically, this causes big trouble. Okay? So the picture in sort of the bottom-up standard model is that you've got an arbitrary 3×3 complex matrix here, an arbitrary 3×3 complex matrix there. Nature just picks some parameters randomly, puts them in the matrix. If you just had this line, you know, you go and you do the thing in the standard model, you diagonalize, you write down the quark mass matrix, you diagonalize it, you have the mass, you know, eigenvalues, and then you get the CKM matrix along the way. If you have these two terms, the down-type quark mass terms wind up looking like the following. So you're going to have the Yij d1 v1 over root 2, okay, plus Yij d2 v2 over root 2, okay, d bar right I d left j plus, I should go plus remission conjugate here. Okay? And this is actually not a problem, right? Here I can just define this whole thing as a big mass matrix for the down quarks, diagonalize it, get the down quark masses, no problem, okay? The problem comes from the fact that if I have, here I have a sum of two 3×3 complex matrices, weighted by some factors v1 and v2. If I instead take the orthogonal combination of those 3×3 mass matrices, there's no reason to expect it to be also diagonal in the same basis that the sum is diagonal, right? And that's going to cause trouble when I look at the couplings of this doublet, okay, the one that doesn't contain a VEV, to down-type fermions. In fact, what I'll generically wind up with is interactions involving, say, the pseudoscalar, for example, or big H, or little h cos beta, okay? Right? Coupling to two different flavor down-type quarks. And I'm intentionally drawing here the diagram for KK bar mixing at tree level through a Higgs, or through a pseudoscalar pull. The reason this causes trouble is that it's in gross violation with flavor physics constraints on flavor changing neutral currents, unless you put some very tight restrictions on the forms of those Yukawa matrices. So there's two ways around this, okay? It's not minimal flavor violation when you do this, okay? So there's two ways around this. Uh-oh, okay. Well, I'll just sort of tell you what they are, okay? The first way around it is called natural flavor conservation. It was invented in the 70s by Glashow and Weinberg and Pascos separately. And they basically said, well, the whole problem comes from the fact that you're generating the down quark masses from two separate terms in the Lagrangian. If you just forbid one of those terms, you're fine. Okay, you're just back to the standard model situation. Same thing with the uptype quark masses, same thing with the charged lepton masses. So the precise statement of natural flavor conservation is that you require that all fermions of a given electric charge, so minus a third, plus 2/3, or 1, minus 1, okay, get their masses from exactly one Higgs doublet. So the down-type quarks, for example, could get their masses from phi 1. There's nothing to stop you choosing the up-type quarks to get their masses from, say, phi 2, or whatever doublet you like. It's just that each set of fermions has to get their mass from only one doublet. That means actually there's 4 physically distinct ways of choosing these discrete couplings, okay? Yeah, absolutely. So if you want to enforce this, you generally enforce it by imposing a symmetry. And the symmetry you generally impose is a Z2 symmetry, okay? Under which, say, you can just choose whatever you like. Say phi 2 goes to minus phi 2, and then you take the right-handed quarks that you want to couple to phi 2 and make them also transform under that symmetry, and you take the right-handed quarks that you don't want to couple to phi 2 and you don't let those transform under that symmetry. In order to keep this working at higher orders, you want to also put that symmetry in the Higgs potential, but it can be broken so-called softly in a way that doesn't cause trouble with the fermion coupling. So it can be an approximate symmetry in the, or what's called a softly broken symmetry in the Higgs potential. I kind of don't have time to get into that, but yeah, you do impose a symmetry, and that does restrict the form of the Higgs potential. So just to give you some naming, the convention is to have the up-type quarks always couple to phi 2 just for simplicity in defining tangent beta, okay? And you have 4 choices. You can have the other guys couple also to phi 2. You can have them only couple to phi 1. You can have the quarks couple to phi 2 and the lepton couple to phi 1. Or you can do this strange thing, okay? These are called type 1, type 2. This is the case in the MSSM, okay? This has like 3 or 4 different names in the literature, but I like to call it lepton specific because it helps me remember that it's the leptons that are special. Specific. And then this one also has like 3 or 4 names in the literature. I like to call it flipped because it's like type 2, except the leptons are flipped down to couple to phi 2. Okay, so those are the 4 types of 2 Higgs doublet models when you ignore neutrinos. Okay, and these patterns of fermion couplings have consequences for the couplings of the physical states to the fermions. I'm kind of running out of time, and I want to spend some time on triplet models, so maybe I'll only just very quickly sketch the couplings of little h to fermions in the type 2 model. And then the rest are in my notes, so you can take a look at that if you want. Right. So the type 2 model, right? The mass of the up quarks, up-type quarks, so up charm and top, okay, are coming from their coupling to phi 2, okay? Which, if I write it in terms of what you would write for the standard model case, I have to put in a sine beta factor. Which means that YU is related to the up-type quark masses by this 1 over sine beta. Okay? And then the down-type quark masses are coming from scalar doublet number 1. Oops, cos beta, okay, which I can write in terms of cosine beta, which means that the down-type quark Yukawa couplings you can write here with this 1 over cos beta factor, okay? This has interesting consequences. So the top quark Yukawa coupling in the standard model is already basically equal to 1, okay? You don't want to make that too much larger than 1, or Yukawa interactions become non-perturbative. 1 over sine beta has the potential to make that significantly larger than 1 if sine beta is very small. That means sine beta can't be too small, and basically this puts a lower bound on tangent beta. Okay? And actually, the way I've defined things, tangent beta always has that same lower bound because the top quark always couples to phi 2. So the top quark always gets a 1 over sine beta in all of these models. Okay? And that lower bound, it depends on how high up you want to be able to run your theory. 0.5 is probably totally fine. 0.2 might be stretching it a little bit. Okay? This thing is also constrained by perturbativity, but this is the bottom, I mean the largest, the heaviest down type quark is the bottom quark. If you put the bottom quark mass here, the standard model Yukawa coupling is pretty small already. It's like maybe 1 over, I don't know, 30 or 50 or something like that. And so cosine beta, it's okay if cosine beta is fairly small and boosts this up. The limit is variously, this gives you an upper limit on tangent beta. Okay. Which is maybe 60 or 70. Okay, again, it depends on how high into the ultraviolet you want the running of your theory to be okay, right? And whether you're doing SUSY or not, okay. Okay, so those are the Yukawa couplings. Now let's look at the couplings of little h, right? And I'm going to use the fact that, well, okay, let me just explain it. Right? So here's the coupling of little h to an up-type quark, so it could be top. It doesn't have to be the actual up quark. Right? I get a minus I. There's an mu over VSM. That's what you'd get in the standard model. Okay? And then there's a modification factor. There's a 1 over sine beta from up there. And then there's going to be a factor which basically tells you how much of little h lives in the doublet that couples to the up-type quark, right? Which is cosine alpha, right? So that's the mixing angle. Okay, so that's the modification factor of the coupling. It's actually illustrative to rewrite this in terms of sine beta minus alpha and cosine beta minus alpha, so that you can see more easily what happens in the limit that little h becomes very standard model-like. And what you get is that. This is much more easy to prove starting with that and then going backwards because, you know, trig identities are like that. Okay. All right, so that's the coupling to the up-type quark. Oh yeah, and notice what happens. When sine beta minus alpha is equal to 1, you just get back the standard model coupling. When sine beta minus alpha is not equal to 1, you get a modification proportional to cosine beta minus alpha and scaled with cotangent beta. Okay. So if tangent beta is large, the modification of this coupling is generically pretty small. Well, you can get a suppression like cosine beta minus alpha. All right. And then the down-type quarks, and I should say the leptons work exactly like the down-type quarks, so I'm not writing them explicitly. Right. So this one has a modification factor with the cosine beta in the denominator, and in the numerator, it's basically the amount of phi 1 in little h, which is minus sine alpha. Okay? And if you do the same thing and write it in terms of those sines and cosines of beta minus alpha, you wind up with the following form. Again, sine beta minus alpha in front, and then you have a minus tangent beta cos beta minus alpha. So when tangent beta is large, this is really interesting. Cosine beta minus alpha can be positive or negative in a general 2 Higgs doublet model. In the MSSM, it's negative, I think. I'm pretty sure it's always negative. So what you can get is if cosine beta minus alpha is not quite 0, okay, and tangent beta is large, you can get a really quite significant modification of the Higgs coupling to down-type quarks, or leptons, okay, even when sine beta minus alpha is quite close to 1, just because you can put a large number there, right, of order 50, okay. Yeah. It just has to do with the property of the mass matrix that mixes little h and big H. I mean, it would take far too long to go into it right now. Yeah, yeah. It just generally happens to come out that way, that you rotate in a certain direction. Yeah. Okay. Yeah. Okay. Okay, so there's the potential for quite large modifications of the light Higgs couplings to BB bar and tau tau in a type 2 model, but not so much for the couplings to, so even when this coupling is close to standard model-like and the WW coupling is close to standard model-like. So this actually gives you some hints as to which couplings you want to scrutinize the most to look for deviations from the standard model in Higgs couplings. Mm-hmm. Basically, yeah, yeah. Well, you can constrain it. Basically, the limit. And so in SUSY, the limit sine beta minus alpha goes to 1. Usually corresponds to taking the charged Higgs and the pseudoscalar and big H and making them all heavy. So you would push yourself into that limit more and more. Yeah. So yeah. But I mean, then you get. I mean, it's that versus naturalness in a sense, because just as it's unnatural to have one doublet really light and one doublet really heavy if their masses of both are coming from the same physics. So. Okay. Mm-hmm. A percent level constraint on this, I think, pushes up the pseudoscalars to the TeV range. Yeah, yeah, yeah. I mean, I can give you references for details if you want. Yeah, yeah, and that's actually. I mean, there's actually this sort of famous interplay between direct collider searches for the pseudoscalar and the charged Higgs and indirect constraints on the little h couplings. Basically, there's a region at moderate tangent beta where it's really hard to detect the extra Higgs states, where instead maybe you go and look at couplings and try to constrain that. Yeah. Yeah. Mm-hmm. Mm-hmm. Oh, you can. Yeah. I mean, beta S. So beta S gamma. Okay. So the idea is in beta S gamma. You can get a contribution from charged Higgs in the loop, and this in the type 2 model gives you basically a lower bound on the charged Higgs mass, more or less independent of tangent beta. I'm not sure I understood your question. I think it's B sub S to mu mu. I think it's that. Yeah, yeah. Yeah, you can. Yeah. In SUSY, it's a little complicated because these are loop-induced processes. You get SUSY particles running in the loop as well, and so you can get partial cancellations. So it's like you introduce more dimensions into your parameter space by that means. So it's complementary, but it's not sort of one-to-one. Yeah. Okay. Okay. So I am nearly out of time, so I want to actually spend some time. Okay. I should say what's the other way. So one is natural flavor conservation. The second option is actually just minimal flavor violation. So basically the idea is that your Yukawa, these two sets of Yukawa matrices that you write down here, you just require that they be diagonal in the same basis, which sounds kind of like a cheat, but the idea is basically that somewhere there's some model of flavor. And if that model of flavor generates Yukawa coupling matrices which are diagonal in the same basis for phi 1 and for phi 2, then you're fine. Okay, that's called. I mean, it's called minimal flavor violation. The simplest implementation is called Yukawa alignment. And that idea is just that Yij d1 and Yij d2 are proportional to each other. Okay? And the philosophical sort of origins of these two approaches are very different. Here the idea is basically that flavor conservation is forced by the properties of the Higgs sector. Here it's that flavor conservation is forced by some model of flavor outside of the Higgs sector and then communicated into the Higgs sector by that means. Right? So yeah, okay. So enough on two Higgs doublet models. I want to try and spend a little bit of time talking about triplets, just because then I can tell you what custodial symmetry is, which I've been asked about a couple of times already. So, okay. Oh, and I should say Yukawa alignment, it basically interpolates between all of these types of models. So you have continuous parameters that for certain values give you back these different models. Okay. Yeah, I'll use this chalk. Okay. Triplets, right. Oops. So in order to make my life slightly more easy, I want to start out by writing out the generic expression for a mass term generated by the covariant derivative, masses for the W and Z, for an arbitrary representation of SU2. Okay. So let me start out with the covariant derivative, and I'll write it in yet another convenient form. Okay, so there's the hypercharge part. And actually, I missed a factor of 2 when in one of my previous lectures. So when writing this in the form of the actual raising and lowering operators, so if you want to correct that in your notes, it's this factor of 2 right here. Right? So that's the covariant derivative as acting upon a color-neutral particle. Okay? And let me look at the generic, like d mu x dagger d mu x type term, where x is some SU2 scalar multiplet, and I'm going to be interested in the v squared term. So I'm only going to take the vev of that thing. Okay? So this term generically looks like, so the little brackets mean I'm just taking the vacuum expectation value part, okay? So I've done some combining of terms already, okay? This is T3, the third generator, quantity squared, okay? Oops, G prime squared, B mu. Here's the hypercharge operator squared. And then there's a cross term when you plug in the covariant derivative here and the covariant derivative there, and you're taking just the pieces that are going to give you v squared terms. There's actually a cross term which looks like 2gg prime b mu w3 mu that doesn't raise or lower your state, okay? Y3, or y times the third generator of isospin, and then here's my other x. Okay? So this can be written in a more general, well, this can be written, I'm writing this in a general form for reasons that I want to be able to just plug in numbers for any representation that I like, okay? The t plus t minus, okay? Here nature is kind to us, right? These are generators of SU2. SU2 is also the group of spin, okay? So all the stuff that you learned in like fourth year quantum mechanics about dealing with spin operators and angular momentum operators and raising and lowering, spin raising and lowering operators and doing all that manipulation carries over exactly to SU2. Okay. So this, you can rewrite them out in terms of T1, T2, combine them up. This winds up being equal to 4 T1 operator squared plus T2 operator squared, which you can write as the isospin vector operator squared minus T3 squared. Okay? And then the isospin vector operator acting on any eigenstate of SU2 is going to give you T plus 1, just like J squared gives you J plus 1 in angular momentum. Minus the third guy squared. Okay? The other trick I'm going to use is the fact that the VEV shows up in neutral terms. So I can use Q equals T3 plus Y to replace T3 when it's talking about the component of X that carries the VEV with Q minus Y. Okay? And Q is 0 for that component because it must be electrically neutral, so I can just replace T3 by minus Y. Right? So this thing here is going to be for T plus 1 minus Y squared. Okay. And likewise, I can replace this T3 by a minus Y and this T3 squared by Y squared. Okay. So if you do that, okay, I'm just barely going to have enough time. So if you do that, all the chalks are really tiny at this point. I'm going to use pink. Okay. So what you do, if you do that, what you wind up with for this term that looks awful. Okay. It's going to contain expectation value of X dagger, right? Contain that. Oops, this is W3. Okay. Plus that, minus 2 GG prime times that, and then expectation value of X. Okay. And these are just the V squared terms. So these are just the terms that are going to give us mass terms. Okay. Now let's look at what these are for the doublet and for the two triplets that I want to consider. Okay. The doublet has hypercharge 1/2. Okay. This first thing, the T plus 1, T plus 1 minus Y squared. If you plug in, this gives you 1/2, and Y squared is 1/4. Okay. For the triplet, there are two triplets. Sorry, there are two triplets I can write down that have a neutral component. I can write down a triplet with hypercharge 0, and then the middle component will be neutral. So this will look like the following. Okay. This first term here, this T plus 1 minus Y squared is going to be equal to 2 in that case, because T is 1. 1 times 2 is 2. Y is 0. Okay? And this Y is 0. Right? There's another triplet I can write down with Y equal to 1, which looks like the following. It has a doubly charged state in it, and the neutral component is in the bottom. Okay, I can also choose Y equals minus 1, but that's just the conjugate of this one. Okay. So T plus 1 minus Y squared in this case is equal to 1, and Y squared is also equal to 1. Right. So what? So now let's look at the contributions to the masses. Oh good, I have more chalk down here. Oh, there's more chalk down here. Good. Okay. All right. So if I take, so basically what I'm going to do is take that expression, pop in the vacuum expectation value as appropriate, plug in the values of t plus 1 minus y squared, and y squared as appropriate as well, and then rewrite things out as a mass squared matrix for the w and the z and the w and the w, the w plus minus, the w3, the hypercharge, okay, those bosons, right? So for the doublet, this mass squared matrix, after taking off the appropriate factors of 1/2 for real states and everything like that, I can write it as v phi squared over 4, where I put a phi to specify I'm talking about the doublet, okay? I'm using the usual 1/√2 normalization here, right? And I can write this as the following form. Okay, zeros everywhere else. Okay, and the basis that I'm working on here is W1, W2, W3, and B. Okay, I should point out W1, W2, they have the same mass squared. The W plus and W minus are just linear combinations of those two. So it's just a little rotation. I'm writing it in this form just because it's more convenient. Okay. This lower block is what mixes the W3 and the B. If you diagonalize this matrix, you'll see that the mixing angle in terms of G and G prime is just what we wrote down before, the Weinberg angle. Okay. And the masses, there's always a 0 eigenvalue. If you just look at this lower 2x2 block and take the determinant is 0, which means there's 1 0 eigenvalue. That's the photon. Okay. And then the other one gives you the Z mass with the appropriate mixing angle. So the mixing angle is theta W, okay? And then the mass of the W is proportional to G squared. The mass of the Z is proportional to what you get when you diagonalize this thing, okay? Fine, right. The feature about this that I want to point out is that if the hypercharge gauge coupling were sent to 0, there would actually be like a global symmetry. The masses of the W plus, W minus, and Z would all be the same. Right? So let me just say that at this point. At this point, it's like, yeah, so what? Okay. So let's do the same thing for the real triplet and the complex triplet. And for the real triplet and the complex triplet, when I write down the, I'm going to let the triplet with hypercharge 0 be real because I can. The triplet with y equals 1 has to have a distinct antiparticle, so I'm going to make it be complex. I'm way over time, aren't I? Okay. Let me just write down the matrices, and then you'll see what point I'm trying to make. So this M squared matrix for the y equals 0 triplet looks like the following. Vev G squared, hypercharge is 0, and the third component of isospin where the Vev is also 0, so you get just zeros down here, right? So this guy is going to generate a mass for the charged W's, but not for the Z and not for the hypercharge, okay? Similarly, for the y equals 2, the mass matrix that you get, let me put a Vev here, okay, is G squared, and then because of these factors, the t plus 1 minus y squared versus the y squared, you actually get some extra factors of 2 down here. Compared to the standard model case, okay? Notice one thing though, the mixing angle of this lower 2x2 block is still theta W, it's still the same thing. But the mass of the Z has been shifted. The photon is still massless, but this gives you too heavy a Z. This gives you too light a Z by massless, okay? So both of these matrices screw up the relationship between the W mass, the Z mass, and cosine theta W. They both also have the property where you no longer have these 3 G squareds along the diagonal. They violate that, okay? If I were to take these two triplets, these two matrices, set the Vevs equal to each other and just sum them, I actually get back a matrix of exactly that form, which is the correct form to preserve the ratio of the W and Z masses. This can be done. You can build a model where you sort of think of these guys in a matrix together. I'll just write this and then I'll stop. Okay. Right? And if they have the same VEV, then the diagonal here is, I mean, the VEV is proportional to the unit matrix here. The symmetry by which you rotate among the W's, okay, can be represented as a global, another global SU2 rotation, which is actually an accidental symmetry of the standard model. When you put in the vacuum expectation value, the SU2 left and this extra global SU2 break down actually to the diagonal subgroup. So if the VEVs here are, you know, the same on the diagonal, you get a residual accidental global symmetry, which is called the custodial symmetry. And that's sort of talked about as a way to ensure that the W and Z masses have the right relationship. So I better stop at this point, and let's maybe we declare coffee, and you can come ask me questions. All right. Okay.